Okay, so good afternoon, everyone. The title of my talk is called Charged Fluids in Higher Order Gravity. So this talk is largely based on a paper that has been published recently. Okay, so in this talk, I'm going to give a brief description of Einstein-Gauss-Bonnet gravity, or EGB gravity for short. I'll provide the background theory and mathematics for EGB gravity, and we'll look at the governing equations for a fluid in the presence of an electromagnetic field. And we'll also look at it in n dimensions. And we'll also look at how an Abel differential equation of the second kind, how it could be solved. And we'll look at the differences between the neutral and the charge case. So we'll look at comparison. And furthermore, we'll look at the effect of dimensions. So spherically symmetric exact solutions to the field equations in any gravity theory are important tools for determining significant insights to compact objects such as neutron stars and black holes. And in particular, charge affects a number of physical features on these astronomical bodies, like the rate of gravitational collapse, stellar masses, and luminosities. Now, some treatments in this direction were considered by Herrera et al. 2011, Torres and Albuquerque 2014, and Mafatikiza et al. 2019, more recently. So therefore, it's important to determine the effects of the electromagnetic field when modeling compact bodies. Now, in general relativity, several charged static distributions have been studied, and these can be attributed to Bonnet 1960, Ivanov of 2002, Gupta and Kumar 2005, and Laguda et al. 2021. Now, fewer results of this nature are known in higher order gravity theories, for example, in Einstein-Gauss-Bonnet gravity, or EGB gravity. Some interesting results of this work are known by Wilshire 1986. This was the first higher dimensional charge analog of the Bonnet metric, and Hansraj 2017 investigated charge static models. And Russell et al. 2022 investigated charge radiation collapse in higher dimensions in EGB gravity. So EGB gravity is one of the most promising theories of high order gravity theories. It is second order Lovelock gravity, and Lovelock gravity is an extension of general relativity to higher dimensions. Now, in this framework of gravity, we have second order equations of motions arising. And furthermore, curvature terms which are quadratic in nature appear as corrections to Einstein gravity. Now, several studies have been conducted in a variety of astrophysical scenarios in EGB gravity. For example, in the context of black holes, gravitational collapse, and static spherically symmetric models. So in a neutral setting, some examples. By Bolo-Andiza, 1985, this was the first higher dimensional static solution. Maharaj et al. 2015 considered static 5-dimensional models. Russell et al. 2018 and 2019 considered gravitational collapse in 5 dimensions and in higher dimensions. And Barr et al. 2019 considered anisotropic compact matter distributions in 5 dimensions. So the aim here is to generate new exact interior solutions for static spherically symmetric models in the presence of an electromagnetic field in EGB gravity in higher dimensions, or n dimensions. So the Gauss-Bonnet action in EGB gravity is provided by equation 1. Okay, so we have n being the space-time dimension, and if we vary this action, equation 1, we obtain the EGB field equations. And Maxwell's equations, so this is given by system 2. We have the EGB field equations and Maxwell's equations. Now, GAB is the Einstein tensor, alpha is the Gauss-Bonnet coupling constant, and the Lovelock tensor here, HAB, is defined in equation 3, with the Gauss-Bonnet term defined by equation 4. So these terms are quadratic in nature. Kappa n here, looking at the right-hand side of this equation, kappa n is the gravitational coupling constant defined by equation 5. And when n equals to 5, it has the form of 3 pi squared, when G and C are considered as unity. Now the energy momentum tensor here for charged matter is defined by equation 6. And EAB is the electromagnetic tensor defined in equation 7, where the total surface area term is defined by equation 8. And once again, when n equals to 5, this form takes on a form of 2 pi squared. Now the Faraday tensor in equation 7 is defined by equation 9. And for the purposes of our studies, we have a non-zero component of the Faraday tensor described in equation 10, where the electric field intensity is defined by equation 11, with phi being the electromagnetic potential. The current density is defined by equation 12, with sigma being the proper charge density.
There was an equation for L.
Sorry?
The equation 1.
Equation 1.
The alpha in the Laplace, there's alpha times LGB. What is the LG?
It's the Gauss-Bonnet term defined here in equation 4. Okay. So for the space-time, we are considering a static one that is of spherical symmetry, and in n dimensions, it is provided by equation 13, where nu and lambda are gravitational potentials that are functions of r, and the n-2 sphere is defined by equation 14. So this is the expanded form of this summation. And when n equals to 5, equation 13 has a form of 15. So now we're going to equate the matter terms to the curvature terms. Okay, so the curvature and matter to obtain the charged EGB field equations, and it is given by system 16, where rho here is the energy density, P is the isotropic pressure, and we have primes denoting differentiation with respect to R, and alpha hat is relabeled as alpha into n-3 and n-4. So these equations describe the gravitational behavior of a charged gravitating fluid in EGB gravity in n dimensions. What we can also see, several terms here appear in green. So these terms represent the Gauss-Bonnet contributions or the higher order curvature contributions. So if alpha hat is 0 and consequently alpha being 0, we obtain the general relativity limit, or the Einstein-Maxwell field equations in n dimensions. Furthermore, we can see that these terms in green add to the complexity of this system. So we want to simplify the system further. So we make use of the transformation 17. And this was first introduced by Durval and Banerjee in 1983. So now the gravitational potentials are now y and z that are functions of x, and the EGB field equations in the presence of the electromagnetic field are now defined in terms of these new variables by system 18, where dots represent differentiation with respect to x. Further note, we can see several n-5 terms appearing and an n-6 term appearing. This tells us that dimension has a significant effect on the dynamics of our model. So when n equals to 5 and n equals to 6, certain terms will vanish. So now we will assume isotropic pressure. So we make use of equation 18b and 18c to obtain the isotropic pressure condition equation 19. So this equation represents the gravitational behavior of our model, and it is a first order nonlinear ordinary differential equation, and it is further classified as an Abel differential equation of the second kind in Z if Y and E are specified. So what makes this an Abel differential equation? It is due to the presence of the ZZ dot term here, the Z squared term here, the Z term, and this inhomogeneous term. So that's how we can identify this is an Abel differential equation. And in general, these are very difficult to solve. We also note several terms provided in green. So this equation, we can see how much of it is represented by the Gauss-Bonnet contributions. If alpha hat is 0, that means alpha being 0, we obtain the general relativity limit. And as you can see, that would be a much simpler differential equation to solve. Sorry, it would be a linear differential equation in Z if alpha hat is 0. Several n-5 terms indicate to us that n equals to 5 is special and simplification occurs. So there will be significant differences for n equals to 5 and for n greater than equal to 6. Now with this equation 19, it leads to a theorem. If the electric field intensity is specified, then the condition of pressure isotropy, equation 19, which is an Abel differential equation, it has to be integrated. However, if we know y and z, then we can obtain the electric field E without any integration process. So it is important to solve equation 19 in order to know more about the gravitational dynamics of our model. Now, in general, it is difficult to solve. However, we can show that equation 19 can be reduced to a canonical form. So we make use of the transformation provided in equation 20, where the new variable W is introduced. Now, this was suggested by Polyan and Zaitsev in 2003. Now, capital W is defined by equation 21. And with this transformation, there are some restrictions. Now, the minimum space-time dimension for EGB gravity is n equal to 5. And we are going to consider n being greater than equal to 5. Alpha cannot be 0 due to this term. 6xy dot plus n minus 5y cannot be 0, this term here. Then with transformation 20, this Abel differential equation 19 reduces to the canonical form in the new variable W in equation 22. Now this is first order and nonlinear in nature. And we have introduced the functions f1 and f0 that depend on the potential y, its derivatives, and e. So these functions have the form 23 and 24. So f1 and f0, and also note f0 only contains dependence on the electric field intensity. So if we remember the canonical differential equation, in general, this is difficult to solve. It's a non-trivial task to solve. As we can see, that the functions f1 and f0 depend on the potential y and its derivatives in a complex manner, as well as the electric field intensity. So a way to solve this equation is to choose a form for the gravitational potential y. So we demonstrate a solution by choosing y of the form given in 26. Now, this choice was made in Hansraj and Kizet 2020 for n equals to 6, and more recently by Naicker et al. 2023 for n greater than equal to 5 for a neutral setting. So further, we then need to specify the electric field intensity, and this is provided by equation 27. So with 26 and 27, where A is the constant, so our charge parameter, capital W is defined in equation 28. It has a simpler form. And equation 25 reduces to the form 29. So this equation is still first order and nonlinear. However, the functions f1 and f0, f1 and f0 are functions involving only the variable x, simpler functions involving the variable x. Now in this form, equation 29 can be solved if we further make a new substitution 30, which then leads to the equation 31. So remarkably, with this substitution 30, we obtain a separable differential equation that can be integrated to obtain the solution 32, where C1 is our integration constant that has to be greater than 0. Now, if we back substitute for W and consequently the gravitational potential Z, we obtain solution 33. So the gravitational potential Z is provided implicitly, however, it's given exactly. So there is no approximations here. And it is defined for n greater than equal to 5. Furthermore, this equation is expressed in terms of elementary functions of x, and there is no general relativity counterpart to this equation. as alpha cannot be 0. Now, earlier solutions are contained in this result. So if we set A to 0, so the charge parameter to 0, so basically switching off the electromagnetic field, we obtain the neutral case or the uncharged case for the gravitational potential Z, and it is given by equation 34. So the gravitational potential Z in this case is given in explicit form, and it reduces to the form in Naicker et al. 2023. So our results regain Naicker et al. 2023 for a neutral case. Furthermore, the uncharged model of Hansrater and Enkiza 2020 is also contained in equation 34 for n equals to 6. So far, the solutions we presented here represent those of a cosmological model or the interior of a charged static star. Now we want to obtain a complete stellar structure. So we would then need to match the interior to an exterior. We need to find the matching conditions or the boundary conditions. So the first fundamental equation is then matching the interior space-time to an exterior space-time at a boundary. So this is what we will consider the boundary. The interior space-time is defined by equation 35 in terms of the new variables x, y, and z. And the exterior space-time is defined by equation 36. Now, this is the Bullower and Diesel voltiometric in n space-time dimensions with capital F defined in equation 37. So matching 35 to 36, we obtain the following forms, 38 and 39. With the gravitational mass m defined by equation 40, and this part of the equation represents the contributions from Einstein gravity, and this part of the equation represents the Gauss-Bonnet contributions. So if we pay careful attention to this term here, if n equals to 5, there is no dependence on the boundary. However, for n greater than equal to 6, there will be dependence on the boundary. Now, the second fundamental form leads to the pressure being 0 at the boundary, and this leads to equation 41. And furthermore, we can see dimension has an effect. When n equals to 5, this term has no effect, but when n is greater than equal to 6, this term has an effect. So simplification occurs when n equals to 5. Now, the total charge at the boundary can be expressed by equation 42, and when n increases, this term will obviously increase. So due to the implicit form of our gravitational potential Z provided, our junction conditions or boundary conditions are incomplete because we need to solve the Abel differential equation of the second kind in conjunction with equation 41. So because we have an implicit form, this cannot be done. So to conclude, we have investigated static models that are spherically symmetric in EGB gravity in n dimensions. We considered the matter distribution to be a fluid in the presence of an electromagnetic field with isotropic pressure. The charge isotropic pressure condition equation is provided by equation 43. Now, equation 43 does admit an exact solution. However, it's implicit. And this can be done if we reduce equation 43 to the canonical form 44 using the transformation 45, where we chose the gravitational potentials Y, 46, and the electric field E in 47, which then led to the implicit form for the gravitational potential Z given in 48. So when A equals to 0, we then regain the uncharged case, which is an explicit form for the gravitational potential Z. Now with that, charge changes the nature of the differential equation. When we have charge, we have an implicit form for the gravitational potential Z. However, it is still provided exactly. When the electromagnetic field is switched off, we then have an explicit form for the gravitational potential Z. Now, our solutions presented here form a basis for studying a gravitating fluid in the presence of an electromagnetic field, and a future endeavor would be to obtain the physical analysis of these solutions, so to obtain the energy conditions whether they're physically acceptable, these solutions. And we also need to complete the junction conditions using a numerical approach. So that means we need to obtain an explicit form for Z in order to complete the junction conditions. We need Z equals to. Thank you, and these are references in my talk.